Very good afternoon and warm welcome to this live session. So here we are going to discuss about the topic that it is titled Poynting's theorem and wave power, and this is the topic belonging to our subject electromagnetic field theory. So this is our 17th live session. Various topics from this particular electromagnetic field theory we have already addressed. So electromagnetic field theory basically can be divided for the study of static electric field and the steady magnetic field, and the behavior of both of these particular fields, electric field and magnetic field, can be together taken into a set of mathematical equations which are known to be the Maxwell's equations. So Maxwell's equation I have already addressed in my previous live session. So considering the use of Maxwell's equations mostly into the point form, which is called as the derivative form, here we are going to have the study of the Poynting theorem. So there it will be the mathematical expression to be derived which is called as the Poynting's theorem here, and then based on to the finding into this Poynting theorem we are going to discuss about the wave power. So let us start the derivation. As we see the title, here it is the Poynting's theorem. So obviously there it is a question, who is this person Poynting here? So this is the theorem that it was originally postulated around 1884, and the name of the physicist is John H. Poynting, and that particular Poynting's theorem we are going to derive here. So basically the motive to have the Poynting theorem is for determining the power flow associated with the electromagnetic wave. So with the help of the Maxwell's equation, I hope we are clear with the behavior of electric field and that of the magnetic field, and that is of course expressed with the help of the spatial derivatives and the time derivatives simultaneously. So now we are going to make first of all the use of Maxwell's curl equation. See, there are two types, Maxwell's curl equations and Maxwell's the divergence equation. So with the help of the del operator, the vector spatial derivative operator, when we have cross product with certain vector quantity, so that is the Maxwell's curl equation, it is associated with the physiological rotation, whereas the divergence equation is with respect to the expansion or contraction. There it is also denoted with the help of the del operator, but with dot in between the vector quantity and that of the del operator here. So here we take the Maxwell's first equation. So here you see on the left hand side we have del bar cross of H bar. So this we can describe as the curl of magnetic field intensity, that is denoted by capital H here. So I am using the bold casing to denote the vectors here, or else you can also put bar over the head of these particular symbolic representations here. So now the curl of the magnetic field intensity capital H is equal to J plus del D by del T. So here it is the partial time differential of the quantity, vector quantity, that it is denoted by capital D. So capital D is electric flux density. So this is the equation from the Maxwell's rate in the point form. This equation you can regard to be the equation number 1 here. Now utilizing this particular Maxwell's equation, we can take the scalar product on both of the sides, that it means on the left hand side as well as on the right hand side. On the right hand side we have the two terms, so that scalar product will be applicable to both of the terms here. So this scalar product is to be carried with a vector quantity that we are well known, that it is capital E, representing the electric field intensity here. So taking the scalar product on both the sides, we get a new equation, and this equation here I can mark like equation number 2. So on the left hand side you see E, that is representing the electric field intensity, is having the dot product. So it means the scalar product with del bar cross of H bar, that it was originally there, whereas the first term will be modified to E bar dot of J bar. The second term it will be E bar dot of del D by del T here. Now after having this scalar product here, we are going to make the use of a vector identity here. So the vector identity, of course, by the use of the two vectors E and H, I am going to express here. So the derivation you can also check into the first chapter of this particular subject. So now you see this is the vector identity where we have dot multiplication with the vector spatial derivative operator denoted by del, with the bracket where we have the cross product of the two vector quantities describing the field intensities of electric and that of the magnetic fields here. So here it is del dot of E cross H here, that is equal to, the first term is negation of E dot multiplication with the curl operation of H added by H having dot multiplication with the curl of E here. So in this vector identity on the right hand side, the two terms involve both of the curl operations associated to the magnetic field intensity and that of the electric field intensity here. So using this particular vector identity that we can regard as equation number 3 here, you can give utilizing into the left hand side of the previous equation, that it was this second equation. Here it is the LHS left hand side here. We get the new equation. This new equation can be regarded as equation number 4 here. So here you see on the left hand side, instead of having E dot of the curl of H here that you see in the RHS of the equation number 3 here, we can express it as H dot of the curl of E minus del dot of E cross H here, and the RHS we keep here, we interchange the order, either you take E dot J or J dot E, it is one and the same here, and the second term on the RHS of the equation number 2 lies also the same. E dot of the partial differentiation of the electric flux density capital D with respect to the time as a parameter here. So let us have this particular equation to be regarded as equation number 4 here. Now next to this, when we consider the another Maxwell equation which is also introducing the curl operation here, the first Maxwell equation that it was del bar cross of H is equal to J plus del D by del T. So this is basically from the Ampere's circuital law, and when we have the similar kind of the operation for the electric field intensity, we have the another curl equation which is from the Maxwell set. Here it is denoted by del bar cross of E bar, that is equal to negation of the partial time derivative of capital B. So capital B is representing the magnetic flux density. So this is also the equation from the Maxwell set we have seen in our previous live session here. Now when we have del bar cross of E bar, that is equal to minus of del B by del T, we can substitute this to the earlier equation that we have regarded as equation number 4. So if this is equation number 5, we can make the substitution from the current equation 5 into the equation number 4 here. So the modified form of the equation number 4 here we obtain, so that we can denote by minus of capital H having dot multiplication with del B by del T. Here it is the substitution, you check the first term on the left hand side, minus we have del dot of the cross product of E and H vector quantities, that it was already in the equation number 4, and this is equal to J dot E added by E dot partial time derivative of electric flux density capital D here. So RHS we keep as it is, and we can put a new number to this equation. Let this, it will be equation number 6 here. We can also have the modified representation of the same equation taking negation of del operator having the scalar product with the bracket that has cross product of E and H, electric field intensity and magnetic field intensity here. So the modified form of the same equation we can also represent here, so that it is negation of the scalar product with the vector operator del and the bracket that has E bar cross of H, that is equal to J dot E added by, here we have epsilon E dot del E by del T added by mu times H dot product with del H by del T here. So on the right hand side we find the three terms here. So here it is the first term, the scalar product of the cross sectional current density J with the electric field intensity, that it is capital E here. Whereas we know the relation between the flux densities and the field intensities here. So if you consider only capital D to be here, D is nothing but epsilon times E. Whereas if you consider capital B, that it is the magnetic flux density, we have capital B is equal to mu times H. So mu is the permeability of the medium and H is of course the magnetic field intensity here. So by the utilization of these two equations having the relation between the flux density and the field intensity, we have this new form of the equation that we can regard as equation number 7. Now in the equation number 7, if you look at the RHS here, as I have already discussed, we have two terms describing the time derivatives here. Now the rearrangement for these two terms we can give by the two new equations. So let us regard this to be the equation number 8 and this to be the equation number 9 here. Now you see, originally here we have epsilon times E into the time derivative, of course the partial, for the electric field intensity. We can take this time differential of the partial type, first of all represented, so del T, and inside the bracket we have here, instead of the epsilon and the E 2 times here, we get 1 by 2 times D dot multiplication with the vector E here. Whereas the similar thing we can do with the last term on the RHS of the previous equation. So if this is the 7th equation, this we can regard as the 8th equation, this to be the equation number 9 here. So in partial time differential of the magnetic field intensity, we take first of all the partial time differential applicable to the bracket. Inside we write 1 by 2 times capital B, that is magnetic flux density having scalar multiplication with that of the magnetic field intensity H here. So having the equation number 8, here it is, and equation number 9 utilized, we can rewrite the equation number 7 and we can put the new number to that particular equation. So let this new equation will be equation number 10, you can write. So this is equation number 10 here. Now in the equation number 10, you see there it is on the left hand side, no change, minus of the vector differential operator denoted by del having scalar multiplication with the bracket that has the cross multiplication of electric field intensity and the magnetic field intensity. This is equal to, here we have J dot E, the cross sectional current density having scalar multiplication with electric field intensity as it is. Now rest of the two terms on the RHS have got changed, and here it is the representation of the right hand sides of the previous two equations, equation number 8 and equation number 9 here. So RHS of the equation number 8 goes here to the second term of RHS of the new equation, and here the RHS of equation 9 goes to the third term of RHS of equation number 10, new equation. Now here we see the del operator. So del operator is a differential operator here. Now here to the equation number 10 that we have at last, we are making integration, and this integral will be a volume integral. So volume integral, it means we are considering the three dimensions into the use. It is triple integral here. So integrating equation number 10, we get a new form of the equation that sequentially we can denote by equation number, let us say this is equation number 11 here. So here you see on the left hand side negation as it is. Here it is the volume integral over del dot in the bracket E cross H. dV is associated with the integral sign here. So on the right hand side, the first term, it will be the volume integral of G dot E dV, volume integral of del T of inside the bracket 1 B dot E dV, and here we have volume integral of del T of 1 by 2 B dot H dV here. So here it is our 11th equation here. Now in this 11th equation, we are going to make the use of the divergence theorem. Divergence theorem we have studied while we learned the electrostatics here, the study of electric field considering no changes into the magnitude of charges, that it was the electrostatics, the very beginning after we completed the vector algebra here. So the divergence theorem is having the relationship between the volume integral and the surface integral here. So if we have consideration of a closed surface, so certain volume that is enclosed from all the sides, so thereupon we can have the volume integral as well as the surface integral for the complete surface that is closed from all the sides here. So that is the relation we know by the name divergence theorem here, and when we make the use of it, and also onto the right hand side, if we change the order of the spatial integration and the time differential, we get the new form here. So I just show you the new form of the equation. Here you can regard this to be equation number 12. So in the equation number 12, what changes have happened? Now you see in the divergence theorem, divergence is denoted by del dot of any vector quantity. So of course E bar cross of H bar, the two vector quantities, when having the cross multiplication, of course the resultant will be a vector. So this is just the representation of the divergence of E cross H here. So utilizing the divergence theorem, what it was the volume integral for the divergence of a vector quantity, we replace by the closed surface area of the closed surface area integral of the same vector quantity, that we are writing to be the result of cross multiplication of E and H here. E is electric field intensity and H is magnetic field intensity here. So this change because of the divergence theorem we have made on the left hand side of the previous equation and got this new form here. Now what we have changed onto the RHS, we have kept the first term as it is. In the second term, what you see, the integral sign first of all, and then inside there it is the partial time derivative for the second term. As well it was the same case, the volume integral, and inside there it is partial time derivative here. We have taken the time derivative outside. Now here it is independent, that is why instead of writing del t here, we are writing ddt here. So ddt, then the volume integral. So volume integral will be applied to 1 by 2 d dot e here dv. Whereas here we see ddt, volume integral will be applicable to 1 by 2 b dot h dv. So this is what the new form of the equation, what we can regard to be the equation number 12 here. So this particular equation number 12 is very important for us, and this particular finding we can get outlined here. So this is what the equation of the Poynting's theorem, and at this stage we can say that the Poynting's theorem has been derived. Now we have to interpret what the information Poynting theorem has provided to us. So in this regard, see on the right hand side we have the three terms. Here it is the first term, here it is the second term, and the third term here. So now you see the first term on the right hand side is the volume integral J dot E dV. So J is a vector quantity cross sectional current density, whereas E is again a vector quantity electric field intensity here. So this is just representing the total but the instantaneous ohmic power dissipated within the volume. I am talking about this because see, E is the electric field intensity. If you check the SI measurement units here, electric field intensity is always measured in terms of volts per meter, whereas the cross sectional current density, if you see, it is measured in terms of ampere per meter square. So for J, there it is amperes, it is current. So for E, it is in terms of volts per meter, it is associated to voltage. So if you remember the Ohm's law, it is giving you the relationship between the current and the voltage, and the constant of proportionality is of course the resistance measured in terms of Ohm here. So the multiplication of the J cross sectional current density in terms of amperes per meter square and the electric field intensity in terms of volts per meter, this is nothing but the total ohmic power dissipated within the volume, because this multiplication is volume integrated for the given closed surface here. So this is the interpretation for the first term on the right hand side here. Now when we talk about the second term you see d dt of the volume integral 1 by 2 d dot e dv. So this second integral is nothing but the total energy stored into the electric field, because both the vector quantities, those are having the scalar multiplication here, are associated to electric field only. Capital E is representing the electric field intensity, capital D is representing the electric flux density. So the multiplication of the two, and there it is division by the number 2, and the thing is volume integrated and further time derivative here. So this is nothing but the measurement of the total energy that it is stored into the electric field here. Next to that we have the last integral. So last integral that has been shown into the third term here. So ddt volume integral 1 by 2 b dot h dv. So the integral part, if you focus, this is nothing but the multiplication of first of all b dot h. So b is magnetic flux density, h is magnetic field intensity. Both the vector quantities those describe the magnetic field. Here they are having the scalar multiplication and the normalization by dividing it by 2, and it is further volume integrated. And then in this term we have the time derivative of the same. So this third integral is representing the storage of the energy into the magnetic field here. So I have shown you the interpretation of the three volume integrals as represented on the right hand side of this 12th equation here. Now let us discuss about the time derivatives here. The time derivatives are at the two places, the second and the third term here. So here the time derivatives are taken resulting to give the time rates of increase of these stored energies within the volume, or the instantaneous power going to increase the stored energy here. So now the sum of the expressions onto this particular right hand side must therefore be the total power flowing into this particular volume, and therefore so as to have the total power flowing out of this particular volume, we can denote it by the help of the mathematical representation, the closed surface integral for E cross H dot ds here, that can be measured in terms of watts here. So for understanding this, whatever the discussion I have made for the three terms onto the right hand side here, that you have to consider here. For the first term I have talked about the ohmic power, the total ohmic power dissipated within the volume. See, this is with respect to the power. Here this is with respect to the storage of energy into the electric field, and after getting ddt it is the power here. So this is also the magnetic energy here stored, and after taking ddt it will be the power here. So power we measure with respect to the watts here. So if you talk about the total power that is flowing out, we need not to take the minus sign into the consideration, as we are talking about the power that is flowing out here. So simply we can denote it by the closed surface area integral for the vector quantity that it will be resulting by the cross multiplication of E and H. So this is of course in terms of watts here. So let us regard this to be the equation number 13. In the sequence we can give equation number 13, the next number here. So now I have made it clear that whatever the total amount of the power that is flowing out the considered closed volume here, enclosed by the closed surface, that has been represented by this much of the representation here. So what is this E cross H here? In the vector algebra we have already studied that the cross multiplication is resulting for the two operand vectors into the another vector. Of course the magnitude you can obtain by the standard formula thereupon we have studied, but as it is a vector quantity it possesses a direction. So if we have the E and H, the directions, so that time in what particular plane these two directions are taken into consideration, the resultant vector quantity because of this cross multiplication will be perpendicular to that particular plane here. And whether that perpendicular direction, of course we will be having the two alternatives here, that can be determined based on to the right hand thumb rule here. So there it will be the vector quantity as a result of cross multiplication of E and H here. So few of the books are referring it to be the capital P here, and they call it to be the Poynting's vector, and few of the books are referring it to be with the help of capital S. So either you denote it by capital P or capital S, no matter, just mention it to be the Poynting vector and keep the consistency of using the same notation throughout your work here. So here I am going to prefer to denote it by capital S. So capital S is simply the Poynting vector. Poynting vector that has been obtained by the cross multiplication of E and that of the H. So as you see, thereupon the total power flowing out a certain closed volume has been represented by the closed surface integral. So denoting S here, what it was, the integral representation in terms of the watts here, here S should be in terms of watts per meter square here, watts per meter square here. So this has to be interpreted as the instantaneous power density, because we are dividing watts by the meter square here. So we regard this to be the instantaneous power density measured into, of course, the watts per square meter here. Now the direction of the vector S indicating the direction of the instantaneous power flow at a point, and that particular direction I have discussed with the help of the right hand thumb rule. So suppose, as obvious, in the electromagnetic wave we are having the direction of E and H to be perpendicular to each other. So for example, if we are taking into the consideration the use of right handed rectangular coordinate system, either you call rectangular coordinate system or the Cartesian coordinate system, it is one and the same here. So if we have x-axis, y-axis and z-axis like this here. So if you take the first vector, that we have the electric field intensity originally directed along the x here, and the second vector denoted by capital H, magnetic field intensity, that is directed along y here. So they are perpendicular to each other. So x is the direction for E and h is having the direction in the y-axis here. They are perpendicular here. So by taking the cross product and having the use of right-handed coordinate system, so we will be having our curved fingers directed from positive x direction to that of the positive y direction. The thumb will be giving us the direction of the resultant cross multiplication. Here you see that it is the upwards towards the positive side of the z axis here. So S will be directed towards the positive Z axis if we have E and H correspondingly directed in terms of X and Y axis here. So this is the discussion with respect to the consideration of right-handed rectangular coordinate system here. So here we just end the discussion with respect to the Poynting theorem, and now we shall be discussing in more details with respect to the wave power here. So we have this particular title, the two parts here. Poynting's theorem has completed. Now we shall discuss with more details associated to wave power here. So as just now I have talked about the E and H directed in the two different directions which are perpendicular to each other. So for describing the perpendicular making 90-degree, another term is also sometimes utilized, that it is normal. So normal direction to a certain plane or a vector quantity, it means it is the direction which is making 90-degree angle with it here. So S we are now going to focus. S is describing the Poynting's vector here. So S is given by the cross product of E and H. So the direction of power flow at any point is perpendicular to both the directions. As discussed, if E is in the X and H is in the Y direction, so we can describe this cross multiplication as EXAX cross multiplied with HYAY, that is equal to SZAZ here. So these are the two unit vectors AX and AY corresponding to the variations of the electric field intensity and the magnetic field intensity here, and capital E suffix X and capital H suffix Y are the mere magnitudes here. So these will be simply the numbers here, the constants here, whereas the directional information is provided by these unit vectors AX and AY. So having the cross multiplication of these two, we get the Poynting's vector. So capital S suffix Z is the magnitude of this Poynting's vector quantity, whereas its direction is denoted by AZ. Now this particular electromagnetic wave will be traveling through various kinds of the material media, we can say. It may be the conductive, of course inside the conductors there it is no the flow of electromagnetic wave, thereupon we have the flow of current. So the energy we measure in terms of the voltage and that of the current here. So volts and the amperes are the two measured units for that particular kind of energy. Into the wired medium, here we say into the wire we have the energy in the form of electromagnetic wave. So for electromagnetic, the two terms will be for electric field intensity and the magnetic field intensity here. So these are of the wave nature. We have a separate discussion already available on the online platform here. So I can treat them to be the E wave and H wave individually here. So if we have the flow of the E and H waves into the various kinds of the material mediums, first of all the consideration of the perfect dielectric. So the best example can be the air, because there it is conductivity sigma is equal to 0, and the permittivity we denote with the help of the epsilon 0. The value is 8.854 into 10 raised to power minus 12 in terms of farads per meter, whereas the permeability we denote with the help of mu 0. The value is 4 pi into 10 raised to power minus 7 in terms of Henry per meter here. So those two constants we have already studied at the time of introduction to the Coulomb's law and the Biot-Savart's law. So here we have the new equations. We can regard this to be equation number 15 and this to be equation number 16, equation number 17 here. So equation number 16 is representing the electric wave here, whereas the equation number 17 is representing the magnetic wave here. The wave nature here we have denoted with the help of the trigonometric function cosine. Inside the bracket we have the angular frequency denoted by omega here, and here it is the time parameter t here, minus the phase shift constant beta, and z is the how much distance it has covered along the z direction here. So it is a spatial parameter here. So similar is the case for representing the magnetic field here, magnetic wave here, and as we have eta denoting the intrinsic impedance, it is basically the ratio of the two field intensities here, electric field intensity and that of the magnetic field intensity here. So having these equation number 16 and 17 representing the E and H field amplitudes here. So we have the power density amplitude in terms of S suffix Z here denoted as. So we have S suffix Z, that is equal to square of Ex0 divided by eta into cosine square of omega t minus beta z here. So the cross multiplication of the earlier two representations here. So here it is the new representation. So this is at the intermediate level to discuss the wave power. You can outline it and give the next equation number. Let us have it to be equation number 18. Now this is the representation of the power density amplitude for the consideration of the perfect dielectric medium. If the dielectric medium is of the lossy type, so Ex and Hy will not be there into the time phase here, and thereupon we will have the representation of Ex as Ex0 into the exponential e to the power minus alpha z multiplied to the cosine of omega t minus beta z here. So for the wave nature there should be a phase shift. So beta is the phase shift constant, and in the practical case the losses occurring, so that it will be accounted by the attenuation constant denoted by alpha here. And for the changes along the axis we have the representation of omega, the angular frequency here. So here if we let the intrinsic impedance eta to be described as the magnitude mod of eta along with the angular information of theta suffix eta. So let this will be the next equation numbers, equation number 19, equation number 20 here. So by using the expression of eta in equation number 20 here, we write the magnetic field intensity given by Hy is equal to Ex0 divided by the mod of eta into e to the power minus alpha z into cosine of omega t minus beta z minus theta suffix n. The new equation number 21 you can take. So by the use of equation number 21 and the earlier equation 19 representing the electric and that of the magnetic waves here, for the lossy type of the dielectric medium here, the power density amplitude can be described by Sz, that is equal to Ex multiplied by Hy. So here it will be Ex0 squared divided by the mod of eta into e to the power minus twice alpha z cosine of omega t minus beta z into cosine of omega t minus beta z minus theta suffix eta here. So here it is the new representation. This we can regard as equation number 22 here. So this will be holding true for the lossy type of the dielectric material medium here. So as we are dealing with the sinusoidal signal represented by the cosine terms here, the time average power density we can denote, that will be described by the next equation here, and this will be the quantity ultimately be measured here. So to find this particular quantity, here we are getting the equation 22 that I have outlined here, integrated over one cycle and further divided by the time period, which is reciprocal of the frequency here. So the use of the vector identity will be there. Here we have a cosine of b, that is equal to 1 by 2 times cosine of a plus b added by 1 by 2 times cosine of a minus b. So the use of this vector identity and the integration over one cycle, we get the respective time averaged power density for this material medium, denoted by this mathematical expression that we can sequentially note as equation number 23 here. Equation number 23. So here we represent the time averaged power density by this particular notation, and inside thereupon we write capital S suffix Z. So here it is equal to 1 upon capital T, integral 0 to capital T for 1 by 2 times Ex0 squared divided by mod eta into e to the power minus twice alpha z multiplied to the square bracket that has cosine of twice omega t minus twice beta z minus twice theta suffix eta added by cosine of theta suffix eta, and outside there it is the representation of differential time dt. So as we see, the second harmonic component of the integrand into this equation number 23, that is integrating to the value 0, leaving only the contribution from the DC component, and the corresponding result we express with the help of new equation. Let us regard this to be equation number 24 here. Average power density, that is equal to 1 by 2 Ex0 squared divided by, we have mod of eta, and this ratio is multiplied to e to the power minus 2 alpha z into cosine of theta suffix eta here. So this particular power density will be attenuating at the rate denoted by e to the power minus twice alpha z. So alpha is the attenuation constant here. Whereas if you talk about separately the electric wave and that of the magnetic wave, there it will be a fall off as the exponential e to the power minus alpha z only. There it will not be the twice of alpha z here, it will be simply alpha z here. So finally the observation we make that the equation 24 that you visualize here can be obtained by very easy method by use of the phasor forms of the electric and the magnetic fields as shown in the earlier equations here into the vector form. The representation here we rewrite, so that we described as the time averaged power density S, it is equal to 1 upon the real part of the cross multiplication of Es with the conjugate of Hs here, and this is measured in terms of, as this is the power density watts per meter square, we can give it sequentially equation number, next equation it will be equation number 25. So in this particular case the Es we describe by the form Es will be equal to Ex0 multiplied by e to the power minus j beta z into Ax, whereas the Hs conjugate, here we have the Hs conjugate involved in the equation number 25, we can give by the next equation. So here we represent as Hs conjugate is equal to Ex0 divided by eta conjugate into the exponential of positive j times beta z ay that we can further express as Ex0 divided by mod of eta into e to the power j theta into e to the power positive j times beta z, and here the direction is given for ay here. So these two equations we can sequentially denote by equation number 26 and equation number 27, which we can substitute into the equation number 25 here. So here it will be a substitution onto the RHS. So this is the very important equation to us that describes the second part of the topic, that it is wave power. So here we are already covered with the understanding of the Poynting's theorem, and now the understanding of the wave power here. So let us have a practice of few of the sample problems associated to this particular topic here. I go for the first problem statement. Before going to the problem statement, I will just show you with the help of the pictorial representation. So if this is the representation of what we have shown for the phasor form of the electric wave here. See, there it is the consideration of the x, y and z, the three mutually perpendicular directions, a part of right-handed rectangular coordinate system here. So the E vector is having the variation along the positive and the negative parts of the x-axis only here. So you see, few of the vectors are upwards toward the positive x, few of the vectors are towards negative x here. So for one wave cycle, we have the representation of the wavelength by lambda here. So anywhere you see at the y is equal to 0 if you have, or at y is equal to certain value if you have, or at x is equal to certain value if you have, the variation is along only the x and x only, positive and negative side. So here it is the electric wave, and here we have the magnetic wave. So here again the consideration of the three axes x, y and z as considered, we have the variation into the magnetic field intensity along the positive and the negatives of the y axis only. So wherever it will be on the x is equal to a certain value, or x and y here we are having originally equal to 0, so at the origin level or at this particular level, you see the variation is along the positive y direction and the negative y direction only. So if we have the consideration of E changes into the x-axis and y changes along intensity h changes along the y-axis, the propagation of the wave along the third axis, which is perpendicular to the both x and y, here it is denoted by z here. So this is the direction of flow of power that is associated to the electromagnetic wave when these two illustrations are taken into together here. So this was the Poynting's theorem and the wave power. So now we go for the first problem to practice for. Here it is the first problem statement. So we have problem statement: if Es is equal to 60 by r sine theta e to the power minus j twice r into a theta measured in terms of volts per meter, here it is the representation, and Hs is equal to, we have 1 by 4 pi r sine theta into e to the power minus j twice r multiplied to a phi here. So if these two representations are given to us, Es and Hs, so Es measured in volts per meter, Hs measured in amperes per meter, the consideration of the material medium in the surrounding for these electric and magnetic field quantities is that it is in free space here. We are asked to find the average power passing outward through the surface. So the surface is defined by the spherical coordinate system parameters here. So r is equal to 10 raised to the power 6. Theta ranges from 0 degree to pi by 3 radians here. In terms of degrees also we can convert, and the phi angle that is ranging from 0 degrees you say, or 0 radians you say. From 0 radians to 2 pi radians, that it means 360 degrees here. So as we want to know the average power passing outwards through the given surface defined by the r, theta and phi for the given Es and Hs, we are going to make the use of the formulation just now we have derived, that it is, so the time average power density here denoted by S, here it is equal to 1 by 2 the real part of the cross multiplication of the Es and the conjugate of Hs here. So for the determination of the resultant, we require Es and the conjugate of Hs. We have the Es and the Hs here. Hs conjugate we can make, and the cross multiplication also we can find out. So for the real part obtained by this multiplication, if we divide it by 2, we get it to the form 15 sine square theta divided by 2 pi r square. The unit vector is describing the direction, that it will be AR. So this is the power density. So it will be measured in terms of watts per meter square here. So as we have the given surface defined by r, theta and phi here, the requested power we can denote with the help of the symbol phi here, and here we have for the integrals onto the surface. So for the surface integral we have double integral. So first of all, for the phi here we have the integral from 0 to 2 pi. For the theta we have integral 0 to pi by 3, and here it will be applicable to the dot multiplication of what we have seen for the S, that we have represented 15 sine square theta divided by 2 pi r square AR dot multiplied with the differential surface defined by the r, theta and phi. Here we have r square sine theta d phi into AR. So there it will be, first of all, the computation of the scalar product, and whatever the outcome it will be integrated over the two dimensions denoted by d theta and d phi here. So to the next step, we get it to the simplified value. So 15 integral from 0 to pi by 3 over sine cube theta d theta here, and this integral, if it is solved and applying the limits, gets us to the stage we write 15 multiplied to the bracket that has minus 1 by 3 cosine theta multiplied to, in the bracket we have sine square theta added by 2, and the limits here we apply 0 to pi by 3. After applying the limits, you will get this stage to 25 divided by 8, and if you find this division, the value it will be 3.13. So of course this is to be measured in terms of the watts here. So this is what the average power passing outward through the surface defined by r, theta and phi. Now in this answer, we have to note that whatever the radial distance is there from the origin, here with the help of the spherical coordinate system defined by the r, so this is basically the radius of the sphere. So as you see, 10 raised to the power 6 is a very large value in terms of meters. So it will not be affecting a lot here. So since we have the power density will be diminishing at 1 upon r square, we have determined this particular answer that you can outline. So this is the answer for the first problem. The problem statement here it is, we were asked to find the average power passing outward through the surface defined by r, theta and phi, and here it is the answer for this particular problem. Now we have another problem that is associated to whatever the understanding we have made by deriving the Poynting theorem and a discussion on the wave power here. So here we start with the problem statement. A 100 megahertz uniform plane wave propagates into a lossless medium for which epsilon r is equal to 5 and mu r is equal to 1. We are asked to find the 6 answers here. So we have parts A, B, C, D, E, F here. In the part A, we are asked to find V suffix P. In the part B, we are asked to find beta. In the part C, we are asked to find the value of lambda. Next to that, we are asked to find the value of ES. In the part E, we are asked to find the value of HS. And at last, we are asked to find the value of the power density denoted here. So here we have, yes, Vp, the phase velocity here. So this is what the velocity we can determine with the help of the formulation for part A. We make the value of C into the U's, which can be denoted by the square root of epsilon r. So epsilon r is the relative permittivity of the medium. So in the given problem statement, that value is equal to 5. So the relative permittivity of the medium is equal to 5. Now C that you see in the numerator, C is the velocity of the light if the concentration of the medium is air or the free space or vacuum you say. So that value is 3 into 10 raised to the power 8 in terms of meters per second. So substituting that particular value to the numerator of the RHS and dividing it by the square root of the 5, it will be holding this particular form. And if you compute the square root and divide it for the 3 into 10 raised to power 8, so we get it the answer for the velocity, that it is 1.34 into 10 raised to the power 8 meters per second here. So here you can outline the answer for part A. So for part A, we have the solution. So we are successful to find the value of the velocity here, that it is denoted. Now we go for the next. So we are required to find beta. So beta is the phase shift constant. So as we have the changes of the phase with respect to the angular frequency omega and the velocity as just now determined by Vp here, we have the formulation beta is equal to omega divided by Vp. So omega is the angular frequency. So omega, the angular frequency relationship with simply the frequency, it will be omega is equal to 2 pi f here. So if we replace omega as 2 pi into 10 raised to the power 8 and divide it by Vp, what the answer we have just now determined as a solution for part A, we get the new equation of this particular form. So 2 pi into 10 raised to power 8 divided by 1.34 into 10 raised to power 8 here. So 10 raised to power 8, 10 raised to power 8 will get cancelled. Pi, the constant you can put 3.14, and if you have the computation of beta, so 4.69 here, and it has to be measured in terms of per meter. So meter inverse you can put as a unit here. So now here you see the answer beta, the solution for part B here. So part B has also been solved for the phase shift constant here. Now in the part to find the value of lambda. So the lambda is the wavelength here. So from the beta we can determine the lambda here. See, beta is here in terms of meter inverse here, whereas lambda we require in terms of meter. It is the distance traveled by the wave for one wave cycle here. So here we have the complete phase for one wave cycle, that will be of 2 pi radians here. So the wavelength lambda will be given by 2 pi radians divided by the phase shift constant beta. So when we substitute 4.69 as the value for beta into the denominator, pi to be equal to 3.14 here, we get the corresponding answer for part C. So lambda it will be equal to 1.34. So this way we have the solution for part C also. You can outline this particular answer here. So out of the 6 unknowns to be determined here, the first 3 unknowns are determined and they have been made knowns here, part A, part B and part C here. Now we focus our attention onto the part D here. So in the part D we are required to determine capital E suffix S. So it is representing the electric field variation here. So if we have the assumption that capital E suffix 0 is the real amplitude and the propagation is into the forward positive Z direction, the polarization for the electric field into the X direction, we write the expression for capital ES that it is E0 into the exponential of, in the bracket we write minus J into beta Z here. The direction it is represented with the help of the unit vector AX, and when we substitute the value of beta here, the expression for ES will be equal to capital E0 exponential of minus 4 times 4.69 Z into AX in terms of volts per meter. So here it is the required expression for ES to be the solution of part D here. Now in the part E, next to that we require the expression for HS here. So first of all, the relationship with the ES and HS we know, that is with the help of the constant of proportionality, what it is, the intrinsic impedance of the material medium here, that can be denoted by eta here. So for the concerned lossless medium, given the relative permittivity and the permeability of the material medium here, we can have the use of eta, that is equal to eta 0 divided by square root of epsilon r. Eta 0 is the intrinsic medium for the free space or the air here. That value we know to be 377 ohms here. So when we substitute that value in place of eta 0 to the numerator and epsilon r, the relative permittivity of the material medium, to be equal to 5 from the problem statement, eta will be equal to 377 divided by under root 5. This value becomes 169 and this is to be regarded in terms of ohms. So as we have, I can say, the conversion factor, if we know the expression for ES with the help of this eta to be known here, we get the expression for HS. So here we write E0 divided by eta into the exponential of minus J times beta Z into AY, the direction perpendicular to the earlier that it was for ES. So by the substitution of eta and the beta, here we get the expression for HS. So here we write E0 divided by 169. This ratio is multiplied to the exponential of minus J times 4.69 Z, the direction given by the unit vector AY, and this is regarded in terms of ampere per meter. So this will be the solution for part E. So here we have HS expression. Now we are left with the last, that it is we require the power density denoted by this notation here for S here. So as we know, in the previous problem statement also we have made the use of the formulation that it was 1 by 2 for the real part of the cross multiplication of ES and that of the conjugate of HS here. So from the previous two D and E parts here, we have the expressions for ES and HS. For HS we can find out the complex conjugate here and take the cross multiplication of the two expressions here. Here we have the two expressions, and for that particular cross multiplication, if you multiply by 1 by 2, we get the power density for S here. So here it will be expressed as E0 square divided by 337. The direction is provided by AZ as a result of the cross multiplication, and the power density measured into meter square. So here it will be the answer for part F here. So here we are covered all the 6 parameters to be computed associated to the given details for the wave propagation here. So this was our problem number 2 here. So after problem number 2, we are going to solve a next problem here. So in the next problem, we are again given the information with respect to the electric wave in the phasor form and the impedance here, the material impedance here, and then we are going to determine the HS and further the power density here. So here we have the problem statement. It starts as given. Here we have E0 into e to the power minus alpha z for the electric wave, which is having the representation as a function of the spatial parameter z and that of the time parameter t here. So here we have expressed as the amplitude E0 into the exponential e to the power minus alpha z, the sinusoidal function sine. Inside the bracket we have omega t minus beta z ax here, and the impedance eta is equal to mod eta into e to the power j phi here. We are asked to find first of all ES, the expression here, then HS in the part B, and next to that in the part C we require the power density here. So this way the short and simple the problem statement here it is. Now what we are going to do for determination of the ES here, we are making the use of the Euler identity here, and this is for the trigonometric function denoted for the sinusoids, that it is sine here. So we can have the representation that we have from the problem statement. So that is equal to capital E0 into e to the power minus alpha z multiplied to the square bracket that has the difference of the exponential e to the power j times omega t minus beta z minus e to the power minus j times omega t minus beta z. This is all divided by twice g here. So this is what the substitution we have made for the sine function representation here. So this is with the help of the square bracket here. So the next type of the representation for the given form will be minus j times capital E0 divided by 2 multiplied by e to the power minus alpha z, further multiplied by e to the power minus j of not the minus j of omega t minus beta z ax, which is added by the constants here. So therefore the identification of the phasor form for the electric wave will be capital ES, a function of z, that will be equal to minus j E0 into e to the power minus alpha z, the attenuation constant alpha, into e to the power minus j times beta z, phase shift constant beta. The direction of this variation for the electric field is the x direction, so hence the unit vector ax, and it is of course measured in terms of volts per meter. So this will be the solution to the part A here. Now after we know this particular expression as for ES, now the computation of expression, determination of the expression for HS becomes simple here. So here we consider the positive Z travel for the electromagnetic wave and the ES along the X direction. So for HS, the magnetic field intensity variation, there it will be the only alternative of the positive Y direction here. So here we express HS as minus J E0 divided by mod of the intrinsic impedance eta into e to the power minus alpha z into e to the power minus j beta z into e to the power minus j pi here. The direction is denoted by ay here, and the measurement unit, it is denoted amperes per meter here. So here I outline the answer for part B. So both the parts A and B we have solved. Now we require only the power density denoted by S. So the formulation is the same that we have made in the previous problem as well. Also we have derived it in this session. So here it is 1 by 2, the real part of the cross multiplication of ES with that of the complex conjugate of HS here. So by utilizing this particular formulation, if we carry out the cross multiplication and multiplication by 1 by 2 here, we get it to the form E0 squared divided by twice of mod of eta. This ratio is multiplied to e to the power minus twice alpha z into cosine phi into the direction, it will be az as a result of the cross multiplication, and the power density is measured in terms of watts per meter square here. So here it will be the solution for the power density as required into the part C of this problem statement here. So after computation of all these, I am going to take the last problem statement to be practiced for the Poynting theorem and the wave power. This is very important topic. More weightage is provided into the examination for this particular topic. That is why one more problem, the last one here. The problem statement is a linearly polarized plane wave in the free space has electric field given by. So here we have the expression. On the RHS we find 25AX minus 30AZ multiplied to cosine of omega t minus 50y. So this is in terms of volts per meter for the electric wave cycle. We are asked to find in the part A omega, the angular frequency, in the part B ES, and in the part C HS, and finally the power density S here. So for the first part, where we require omega to be determined here, we can get to know the phase shift constant beta, that we can represent sometimes by k0, which is equal to the angular frequency omega, which is to be computed, that is divided by the velocity of the electromagnetic wave into the vacuum or free space or air, that is denoted by small c here. So from this particular formulation, substituting the value of c, 3 into 10 raised to the power 8 meter per second, we can write omega is equal to, here we have 50 into 3 into 10 raised to the power 8, the value it will be 1.5 into 10 raised to the power 10 in terms of radians per seconds here. So here it is the answer for part A of this problem statement. So omega is known to us. Next to that we require ES. So from the given expression we write ES is equal to, here we write 25AX minus 30AZ exponential of minus j into 50y here in terms of volts per meter here. So here it is the answer for part B here. Now for part C, we are making the use of the fact that each of the components to ES, there it will be the perpendicular, oppose, orthogonal we can say in terms of the vector algebra. HS component here will be oriented such that the cross multiplication of this ES and HS will be into the direction of propagation of the electromagnetic wave. So consideration of this particular understanding, we write the expression for HS, that is equal to minus 1 upon eta 0 multiplied to the bracket that has 25AZ plus 30AX multiplied to e to the power minus j 50y here. So here it will be the answer I outline for part C here. And for part D, as we require the power density here, the same formulation that we have derived, so that we have here utilized, and we have found the answer here. So here we have 1 by 2 real part of the cross multiplication of ES and the complex conjugate of HS here. So here we obtain the cross multiplication, and finally the calculation gives us the answer for power density S is equal to 2.0 AY in terms of watts per meter square here. So this way we have derived the Poynting theorem in this live session. We have discussed the expressions derived into the Poynting theorem associated to the wave power here, and utilize those expressions as the formulations to compute the necessary parameters asked into the problem statements. So four problems we have practiced here. So a lot many information into the details with respect to the subject electromagnetic field theory we have available on our online platform. So you can subscribe to those lectures and get all of your concepts related to this particular subject cleared and score good marks into the examination here. Thank you.